Hello everyone, my name is Cherie Ledoux and I'd like to welcome you to today's training webinar, Vulcan 10 Unfolding Tools. Your host today is Matthew Deutsch. Matthew is a special applications development engineer who develops software in mining engineering, computer-aided design, and geostatistics. A few things before we get started. First, today's webinar will conclude with a question and answer session. So please feel free to write questions in the panel on the right-hand side of your screen. Also, we have created an unfolding training group in the users area for this course in which supporting documents will be found. You will receive a link to access this group along with a recording of this webinar by email. I'll now hand it over to Matthew.
Okay, thanks, Cherie. So today we're going to be looking at unfolding in Vulcan 10. So we're going to talk briefly about the various different unfolding methods in Vulcan, as well as some of the improvements which have been made for Vulcan 10. There are several different techniques which all have different applications that all live under this unfolding banner, but they all operate quite differently. This is a training webinar, so I'm going to spend a bit more time actually explaining the different options and functions, but this is a really complex topic, and 30 minutes is really not enough time to give more than just a cursory overview, really appealing to your intuition, not a deep understanding of the topic. So, however, if you're interested, you should check the training calendar or contact your local Maptek office for more details. Okay, we do have a short poll, which we can start up now, and the question is, of the following unfolding methods, which have you used? So I want to see kind of what people have been doing in the past, so projection, bend, LVA, alternative search. You could also indicate ones that you're more interested in, if you'd like. Okay, but before we dig into the different unfolding methods, we should ask ourselves, what is unfolding? And why would I want to do it? Well, in Vulcan, unfolding refers to a set of tools for injecting your geologic knowledge into your geostatistical modeling process. Unfolding techniques allow you to model complex geology more accurately and easier than before, either by identifying local changes in geology, adapting to those changes, and really generating a better model. There are many different techniques for unfolding, such as the easy-to-use and understand alternative search ellipsoids, through projection and bend unfolding, which modify coordinates on the fly based on your geologic interpretation, to the much more complicated but extremely powerful locally varying anisotropy. As to why you would want to perform unfolding, well, it can improve your models. Applied correctly, unfolding should improve the tractability and believability of your models, and should improve reconciliation and just all-around model quality. However, unfolding is not a panacea. It has to be applied in certain contexts, and special care has to be taken to set the other parameters correctly. I'll touch on some of these areas throughout the rest of the webinar. Okay, but before we get to that, let's see, do we have any results from the poll that I could see? Okay, looks like a lot of people have responded with projection unfolding, and some more with bend, and a lot less with LVA and alternative search. And some of you haven't done any yet, and that's good, because now we'll get a better overview. Yeah, projection is definitely the easiest to apply, LVA the most complicated, but I'm surprised to see alternative search so low, but I think I know why, and we'll cover that as we get there. We can, in Vulcan 10, it's been vastly improved. Okay, thanks. So unfolding, right? It's a collection of tools and techniques. It's not just one thing. So we have our projection unfolding, bend unfolding, and locally varying anisotropy, and those really fit in your create unfolding model. Then we have the anisotropy model, which is your create anisotropy model. once you've created these unfolding things, you've used these tools and techniques, you can then use the results in several different options. So you can apply any of those unfolding methods to estimation and simulation, and then you can apply the unfolding models to variography. So we'll look at, to begin with, those unfolding models. So this lives in Vulcan under the menu Block Unfolding, Create Unfolding Model. What this does is it creates a .tetra file. You can think of this as your recipe for how the unfolding should be done. It doesn't actually do the unfolding. It just tells these other options how to do the unfolding. So there are three different unfolding model types: your projection, bend, and locally varying anisotropy, and we'll cover those all in some detail. The tetra, the .tetra file that this option creates, is then used in these other options. So, for example, on the left I have the panel for the create unfolding model, just for creating a bend model. So all you have to specify is the top, the bottom, the step size, and then the bearing and a plunge for your preferred major direction. That will create this bend model.tetra. Then on the right I have two examples of where you put that information. So when you go to the estimation editor, you're going to specify in the search region, hey, I want you to unfold and I want you to use this recipe. And then also in the new data analyzer in Vulcan 10 for variography, you're going to specify, yes, I want to do unfolding and here's my recipe. So that's really what the unfolding model is. It's this .tetra, which then is used in these other options. So the first technique for creating that .tetra is your projection unfolding, and this was the one that over half of you said that you've used. Projection unfolding projects your coordinates into a new coordinate system. Now in Vulcan 10 it can project to an arbitrary plane. Let me show you what I mean by that. It takes a top surface, a bottom surface, and a plane. So let me just switch over here, and I'm going to try and draw a little schematic for you of what the projection unfolding sort of looks like. So let's imagine that you give it a top and a bottom surface. And let's imagine that we're looking kind of, this is our X and this is our Z direction. We're also going to supply a plane. So this is your input, and that specifies enough to how we're going to do the projection unfolding. Imagine that we have then some samples kind of coming through here or something like this. What happens to those samples? And then imagine, I'm not going to draw a million blocks, but we have blocks everywhere as well. What happens to those block coordinates in the estimation? Well, it's quite simple. Everything is just projected straight down vertically, normal to our plane, to lie in a new coordinate system on the plane. So let me draw that here. In the case of projecting straight down, X is going to remain the same, but the Z, your Z coordinates, are going to change. And they're going to change in a specific way. Every point which is on your bottom surface here, let's label this point as A, he's going to get projected straight down. His X coordinate would remain the same, but his new Z prime coordinate would be a 0. So every point that's along the bottom surface gets the same Z prime coordinate of 0. So let's say, imagine we label this guy as B. He's also going to be at a Z prime coordinate of 0, even though their real world Z coordinates are somewhat different. Similarly, any points which are on the top of your surface will get a new Z prime coordinate of 1. And anything that's, in the middle will be scaled. So this guy here, he might get a Z prime coordinate of 0.5 or something. And anything that's, say, above your surface would get a new Z prime coordinate that's greater than 1. And anything below would get a Z prime coordinate that's negative. Okay, but everything gets projected straight down, normal to the plane. Now in Vulcan 10, you can project to an arbitrary plane. So imagine that you have a more steeply dipping sort of deposit, probably a vein type deposit or something like that. You can project to a plane which is angled like this, in which case your points will still be projected such that any point that's along the top will have a new z prime coordinate of 1, and anything that's along the bottom would have a new z prime coordinate of 0. But now, instead of everything getting, say, projected close together like this, they're going to be projected farther apart, which makes more sense geologically. So projection unfolding is easy to use and easy to apply, and is really easy to reconcile. It's easy to understand. It's very clear exactly what's happening with projection unfolding. But there is a slight drawback. You can imagine, what if we had an input surfaces something that looked like this, and we were going to apply projection unfolding, say, straight down. All of these points here would end up right on top of each other in our projected space, and that's not ideal, right? What we would prefer is for some kind of unfolding that will allow us to sort of look around these corners, or to handle more complicated surfaces, more complicated geology. And projection unfolding won't do that, but bend unfolding can. So let's jump back into our presentation here. So bend unfolding, as its name suggests, bends your coordinates into a new coordinate system about each block or point individually. So again, the input is similar. It's a top and bottom surface. You have to supply a step size and a major direction, and the output is the same. You get a dot tetra file, which then you can use. But bend unfolding operates differently. Let me draw a little example with that same sort of surface here. So let's imagine that we had some kind of surface like this, and let's imagine that we were estimating a block which is right at this location here. And we have some samples here. Just draw a few going through, like this. Let's imagine. So we have some samples here. Maybe I'll add another sample there or something. And we would like to estimate this location. The first step of bend unfolding is that this location, this block, is now going to become the center of our world. It's going to be, this is our new center in the new x and y coordinates. Its z coordinate will be similar to projection, that any point which is along the bottom will have a new z coordinate of 0, and anything along the top would have a z coordinate of 1 in our new space. But we're going to determine new relative x and y coordinates for every point by walking along our surface. So we can imagine that we sort of walk over here and we find this guy. It's like, okay, well, I'll put him there, which is the same sort of walking away. And then we'll put another one here and there maybe. And then we start walking this way, and we have to walk quite a bit farther, so maybe that ends up out there in our new coordinate system. And then everything will happen in this new unfolded bend coordinate system, which is unique to this block. When we then turn around and say we want to estimate this block, everything, that entire process will be repeated again, and the samples will be unfolded relative to that block. So one way you can think of bend unfolding is you can kind of imagine it like, I'm not an artist, but we got maybe a hand here and another hand here, and we kind of pull our surfaces apart and sort of flatten them down about some middle point, and that will kind of, at the end of the day, you'll end up with this new coordinate system, okay? And that's what bend unfolding does. So bend unfolding can, quite literally, look around corners and around bends, and it could even look around all the way that way, okay? So bend unfolding can be much more flexible. It can handle more complicated deposits, but at the cost of additional complexity and at the cost of additional time required in a computer sense. It takes longer to run than the much more simple and easier to understand projection unfolding. Okay, the next one is your LVA unfolding, and this is much more complicated, and I'm not going to be able to do it justice in this short amount of time. But it's going to take your coordinates, your real coordinates, it's going to take them and an anisotropy model, which I haven't really talked about yet, but we're going to talk about in just a couple minutes. An anisotropy model is a block model with 6 variables, your bearing, plunge, and dip, and a major, semi, and minor. And these indicate on a block basis what the major direction of continuity is, as well as the relative, it's very continuous in this direction and less so in that, as well as that information. And it will elevate your coordinates into some different space. So I'm not going to do it justice, like I said, but I am going to try and explain through the means of somewhat of a synthetic example where this would be appropriate. So let's imagine that we have a deposit here, and we're looking in section view, and maybe it's some kind of copper pipe deposit where lava has come up and brought metal for us. You'll have to forgive me. I'm more of a math guy than a geology guy, so you'll have to look past my poor explanations. But we have a deposit where the geometry of the deposit in a geologic sense, if we cut a section through here, say, and we're looking at X and Y, due to various kinds of zonation or other sorts of geologic processes, things are more continuous along the periphery of our pipe. So, and things are more continuous in this sort of circular kind of fashion. So a point that's right here, let's say A, could in fact geologically be closer to this point B than it is to the point in the middle of them, C, here. So of course not in a Euclidean or a geometric sense, but in a geologic sense, A could actually be closer to B in terms of its properties than it is to C, because these were perhaps deposited or cooled down at very different times. So there's no way that we could make A closer to B than it is to C through projecting to any sort of plane. That's not going to work, no matter which way we project. Or even bend unfolding can't handle this sort of thing. But LVA unfolding can. So you have to tell it. So you're going to give it, for every block, you're going to give it these sorts of ellipsoids, which specify things are much more common in this particular direction and with this sort of range. And what it will do is it will use that information along with a technique called multidimensional scaling to give you new coordinates for your points. So one way we could kind of imagine this, I realize that it's not completely the best way, but let's imagine that we cut a section through those points, and I'll just draw that over here, and then let's say we put A here, C in the middle, and B on the side. How could I make A closer to B and farther from C? Well, you could imagine folding that line up, say through, and this is a one-dimensional line, let's fold it up and through the second dimension, and let's just put A here, B here, and then C at the bottom. And we've kind of cheated. A is now closer to B than it is to C, and so on. And you could imagine in this sort of case, if you had a napkin in front of you, you could kind of bring the corners of the napkin together and sort of fold things up that way through a higher dimensional space. And that's perhaps one way that you can begin to understand LVA unfolding. Of course, it's very complicated, and it takes a lot of time to get it set up correctly. And it's not it shouldn't be used for, vein type deposits or anything like that. It's much overkill. It's more for these really highly nonlinear deposits. Okay, so let's talk about that input though, that anisotropy model, and where it comes from. And now in Vulcan 10, the new ways that you can get it. So like I mentioned, that anisotropy model is a block model which defines a bearing, plunge, and dip and a major, semi, minor as variables, which the bearing, plunge, and dip describe the orientation, the major, semi, minor describe the anisotropy, and there are several different methods for creating this anisotropy model. Before in Vulcan 9, you could use one or two surfaces. Now in Vulcan 10, you can use ellipsoid, which I'll demo to you in just a minute, or a continuous variable. Once you have that bearing, plunge, and dip, major, semi, minor, you can then use that information in a couple different places. So of course, like I had just mentioned, you can use it to create your LVA.tetra file, but you can also use it just directly in the grade estimation editor, as I'm showing on the right, to specify for each block a custom search ellipsoid, a bearing, plunge, and dip, major, semi, minor, instead of having one global search that can vary by block. And now you can create that model much easier, so I expect now you can use that sort of method and hopefully improve your models. So let's look at how we can create it. There's a couple different ways that I mentioned. So from a single surface or two surfaces, let me just draw that out really quickly here. So you could imagine that you give it this single surface, and it's going to say for every block, okay, so we're going to kind of follow along that surface, and and then this block looks like that, and this block like that, and so on. So it will specify that those bearing, plunge, and dip for you on a block basis. So that way you could then say, when I'm estimating this block, I want you to search, say, like that, and when I'm estimating this block, I want you to search in that direction. And you can do that with one or two surfaces. You can also specify from a variable. So this uses a moment of inertia technique. This is new in Vulcan 10. So you supply a continuous variable and a window size, and it will come up with an anisotropy model for you from that. And what I'm going to demo right now is creating that anisotropy model explicitly from user-defined ellipsoids. So you can supply those ellipsoids from design data, triangulations, or interactively, and then it will fill in an anisotropy model for you. So let's look at one example of that. You could, well, where I'm going to demo it, but you could imagine that there is some complexity required, because if you have an ellipsoid that's like this, say at 10 degrees, and then you have another ellipsoid that's pointing, say, that way at 350 degrees. If you tried to just average those naively, you might say, well, 10 plus 350 over 2 equals 180, but oh man, whoops, you're pointing in the wrong direction in that case. So there's a little bit of complexity required to make it work in all three dimensions and so on and average smoothly. Okay, let's jump into Vulcan and let's see that in action. So I have Vulcan here. I'll just load up the block model that we're going to be looking at. I'm just going to show in 2 dimensions. So let's look at block unfolding, create anisotropy model. So this panel is new in Vulcan 10. So we can fill out some spec file and some identifiers that you could run different zones, or you can keep things in spec file. Let me select my block model. I'm just going to show the ellipsoid method in this case, and I'm going to fill out my output first, just so that we don't have to fill it out again. So I need to specify where I want things to go, and in this case I have 6 variables in my block model where I want these results to go. Then I can click on the particular method that I'm interested in. So we're going to look at from ellipsoids. So let's just draw some ellipsoids. So you can say interactive, you can pick a point. Maybe I'll have him pointing that way, and I'll put an ellipsoid there. can click interactive. Maybe I can add another one, maybe him pointing, I don't know, that way. And then let me add just one more over here, say pointing like that. So once I've defined these ellipsoids, I can just hit apply and run. And it went and populated my block model. So now let's look at those results with block viewing, load dynamic model. So I've already kind of filled this out. The important thing is to display anisotropy vectors. So this option you need to specify your bearing, plunge, and dip, and we'll display the first axis in black. So we'll look at those directions. So if I hit OK, we can see this is the anisotropy model, which it has interpolated for us. So you can see that things smoothly vary between these ellipsoids, which I've specified. If I don't like a particular area, I can click interactive again, and I can add another ellipsoid in that spot, say, hit OK, run it again, and then I can reload that model just very quickly, and we can see how it's adapted to the addition of this new ellipsoid. Of course, specifying ellipsoids interactively is fun, but another good way of doing this is by using design data. So I'll just remove those ellipsoids, and I'll clear my grid off here, and I'll actually also remove that. Okay, so I can draw, just with design data, some sort of set of lines, and I can import those here. So I'll just do that. I'll select that object, that one. And now when I hit apply and run, it goes off and it went and did its thing, whoops, and then let me load that model. It's created this new anisotropy model here, and I can use that for LVA or for locally reorienting my search, which I called alternative search. Okay, so let's jump back into the presentation really quickly here. So I showed a quick live demo, and now I'm going to turn it over for questions. I might have gone a little bit over my 25 minutes, but hopefully we still have some time for questions, so feel free to type them into the panel on your right. Like I said, this has been a bit of a whirlwind, very quick sort of overview of these deposits. So if you need more information, the users area group has been created, so please feel free to go there and type them in, and I'll respond to all questions in that area afterwards. Okay, thanks. Sorry, I'll turn it over to you, Cherie.
Great. Thank you, Matthew. Really good information. As I mentioned before, and Matthew just mentioned also that you can write your questions in your panel on the screen, and it looks like we do have a few already. The first one I have here, Matthew, is how many triangulations can be used to define an ellipsoid model?
Yeah, great question. You can use, I didn't have time to cover that at the moment, but you can actually import a triangulation directly and it will create a ellipsoid for every triangle and then fill things in between that. So you have to be careful to give it a triangulation that's not, say, 1,000,000 triangles, but you can import any number of triangulations and have the new ellipsoid method interpolate between all of your triangles.
Okay, next question. How do the unfolding models get applied during conditional simulation?
Yeah, in conditional simulation, what we've started implementing all of the unfolding in simulation, and right now you can use bend and projection, and you can also use the alternative search. You cannot use LVA unfolding yet. It's a bit more complicated and requires lower level changes. But other than that, the unfolding can be applied directly in simulation as if it was grade estimation, just by supplying either the dot tetra or your alternative bearing, plunge, and dip major, semi, minor.
Okay, next question. How do the plunge angles get populated? She says she understands the dip and azimuth.
Yeah, great question. So I kind of glazed over that. For the ellipsoids, you can specify them directly. So let me actually jump back into Vulcan and show. So you can specify bearing, plunge, and dip directly in the grid, and it will smoothly interpolate in 3D. I've only showed a 2D model, but it will do everything in 3 dimensions. It'll smoothly interpolate them. When you're coming from design data, however, a single line only defines 2 of those angles. It doesn't define the third. So in the import option, you have to specify a plane which will be used to get that third direction.
Okay, here's another one. Is training offered for unfolding? You kind of mentioned that before, Matthew, but I don't believe we have anything on the calendar.
Yeah, I don't think there's anything on the calendar. Normally this unfolding training is done by request. We did offer just recently a 2-day unfolding training for when Vulcan 10 came out, and and of course if there's more interest, I'm sure we'd be willing to offer it again. Other than that, you can add on a day of unfolding to any sort of geostatistics training, or just take a day yourself, like by itself. So feel free to contact your local Maptek office to get more information on that.
Okay, we're going to take one more question, and then we're going to have to close out the webinar. There's a bunch of them coming in, but so the question I have here is from Paul, and he asks, is the z-value in projection still a number between 0 and 1? Is there any way to use a real z-value instead of a fraction? For example, in areas where the top and bottom surfaces pinch and swell, the relative z-value would fluctuate.
Yeah, that's a really good question, and the way that I normally handle that sort of thing was, so let's imagine the z values will be between 0 and 1, such that maybe that's not the best drawing, but they will be, but values that are on your bottom surface will have a z value of 1. Samples that are on the top will have 1, things above greater than 1, things below negative. What you would do if things pinch together, and you don't want these sorts of things being projected to exactly the same sort of z values, is I would supply a representative top surface instead of the actual top surface, and this could simulate a sort of erosion in this particular case for the z values. So in this case, by supplying a representative top surface, I'm able to have that sort of control that you're asking for.
Great, thank you, Matthew. So as I mentioned, we are running out of time today, and there are more questions coming in. We will answer those questions offline. If you come up with additional questions later on, please feel free to post those in the training group that we mentioned. You will receive a link to that after the webinar, as well as a recording of today's webinar for reference. So if you are not a Maptek client and don't have access to the users area, just email solutions@maptek.com, and we'll ensure that your questions are answered. On behalf of the entire Maptek team, I'd like to thank you for attending today. Please visit maptek.com/webinars for a complete list of upcoming and recorded webinars. Thank you, and have a great day.